So now let's finish up the last direction in our proof. So suppose we know that the reduced C-star algebra has a character. So let's use notation tau from the reduced C-star algebra of G to the complex be a character, basically a continuous multiplicative function, unitole. And the good thing about the reduced C-set algebra is that it's sitting inside a really concrete Hilbert space. Okay, so it's sitting inside the B of the L2 space of G, and because here is the discrete, so L2 is just you can treat it as a Hilbert space viewed from an orthonormal basis delta of G. So each element in G, you have a orthonormal vector, and then you take their completion as the L2 of G. So the the reduced C-star algebra sits in there. Okay, so now because you have a character, it's basically it's going to be positive and multiplicative and so on. Well, now you have it on a sub-algebra, and it's sitting inside a bigger algebra, so you can use the Harmonic extension. So by the Harmonic extension, I can extend it to, well, may not be multiplicative, but at least I can make sure it's positive on these positive operators. So there exists a extension, as they call it, phi, from the bounded linear operator on the L2 of G to the complex. That's going to be, let's say, going to be, first of all, such that, first of all, phi is an extension. So if I restrict myself to the reduced C-star algebra, then I get the tau back, and then phi is going to be positive. Okay, so maps positive operator positive. All right, so I want to, first of all, let's try to think about using some multiplicative domain argument. So one thing is that if you have a positive operator, a positive functional from some C-star algebra to the complex, then automatically this is going to be completely positive. This is some facts about UCP maps. I'm not going to prove it. So this is, and hence UCP actually. Okay, the unitole is really because when you restrict to the reduced C-star algebra, it has to be unitole because your tau is a character, so it's unitole. So now you have a UCP map from a C-star algebra to another. And you can apply the multiplicative domain argument. You can look at all the elements where phi a star is equal to phi a and phi a star. And the good thing is that that's going to contain your all the left regular representation. Basically contains your the reduced C-star algebra. Well, partially because you reduce C-star algebra itself, the tau is a multiplicative on that part, so your phi is multiplicative on there. All right, so this is, let me write this argument down. So for every s inside G, if you consider phi of the lambda s star, okay, so this one is going to be equals to, well, because lambda s and lambda s star, they're in the reduced C-star algebra, that's going to be equals to tau of lambda s star, but tau is multiplicative, it's a character, so this is tau of the lambda s with tau of the lambda s star, the whole thing star, and you can write it as phi of lambda s, phi of lambda s, whole thing star, all right? And you do the other way as well. So the idea is that the multiplicative domain that's going to contain all of these lambda s, so because it's a C-star subalgebra, contains all the lambda s, I have this is of course, containing actually the reduced C-star algebra, okay? So in other words, in particular, I have for every, say, x inside the bounded linear operator on the L2 of G, if I want to compute a lambda of, say, lambda s with x times, say, lambda t on the other side, I can move the lambda s, lambda t outside. Okay, so I can make a lambda s phi of x, phi of lambda t. Okay, so that's for all s and t inside G, and for all x in the B of L2. Okay, that's the multiplicative domain argument. And now we'll see why this is very powerful. Okay, so this phi is built on the bounded linear operator on the L2 space. And inside there, well, I want to manufacture a left invariant mean, so I need a functional on the L infinity space. And the L infinity really sits inside the B of L2. The reason is that for every f inside the L infinity of G, it really sits inside B of L2 of G by this multiplicative map, or you can think about this diagonal map. So you map f into this operator M of f called multiplication operator. So the MF, if you take a L2 function, is just you multiply by f, okay? You always have, this is going to be bounded, the norm, the operator norm is going to be bounded by the infinite norm of f, okay? You just take the, if you think about computing the L2 sum, L2 norm of the multiplication, each entry gonna multiply by the f of that entry, and then, but the f is bounded by its infinite, the sup norm. So this map, you can clearly see why it's going to be inside, it's bounded, okay? So I have the M of f is, the operator norm is bounded above by the infinity norm of f, okay? So you do have this f L infinity sitting inside the bounded linear operator on L2 of G. So you can just define kind of the phi of f. You define it to be the phi of the M of f, okay? So that's going to be a functional on the L infinity space because your phi is a functional on the bigger one, the B of L2 of G, okay? So defines a phi inside L infinity of G basically defines that, okay? And in particular, if you define it this way, so if you just take the constant 1, okay, that's going to be equals to, well, if you think about what happens to the constant 1 function, you multiply every entry by 1. So that's the identity operator. So it's the phi of an identity, which should be equal to 1 because the identity is inside the reduced C-star algebra. So your tau maps is to 1. So this is 1. Okay, so this phi is going to be really a mean, okay? And we want to show that this is, well, phi, of course, is going to be positive on positive thing. So this is really a mean. And we just need to show it's actually left invariant. And to show that, I need to think about what happens when I try to left translate my function by s. Okay, so if I want to consider what's the multiplication map by left translation of my function f applied to g, let's say if I want to evaluate t, so this is just no other than the left translation of f evaluate t multiplied by g of t. So this is f of s inverse t, g of t. And you can treat this as the following. So you can think about you're not multiplying f, but you're not multiplying f on g, but multiplying on a translation of g. Okay, so you can think about it as a translation by lambda of something evaluate at s inverse of t. So make these both s inverse. And to do that is, you can say this is essentially a left translation. Basically, use the left regular representation, translate by s inverse. All right. S inverse, there's another way. Sometimes you can also write it as star, lambda s star. Okay, it doesn't really matter. But in any case, this one you can now treat it as you left translate this whole thing. Okay, you left translate this whole thing f of t times the lambda s inverse g of this t. Okay. So what you end up with is it's basically a composition of these functions. So you can think about it as you translate your g by s inverse first, and then you multiply the f, and then you left translate everything by s again. Okay, so these two are the same. So basically what I have is that m of the multiplication of left translation of f can be written as a combination of the multiplication by f with some lambda s and lambda s inverse. Okay, it's a conjugation. All right, and now because of that, if I want to evaluate phi of the left translation of f, and by definition, this is, well, this is just basically what I mean by that is phi evaluate on this bounded linear operator on L2, the multiplication map. This is also going to be equals to lambda s mf lambda s inverse. But because your lambda s is in the reduced C algebra, use the multiplicative domain, so you can move them outside. You can have phi of the lambda as inverse, all right? And you have phi of MF in the middle. But these two will multiply to 1, okay? You realize, well, phi is a functional, so these are complex numbers, so now you can move them around, okay? So you group them together, you have a lambda s, phi of lambda s inverse, or it's just really because it's unitary here, so it's a lambda s star. And then you have the phi of MF, and they multiply to phi of lambda s star, which should give you 1, okay? So in the end, this is just going to be equals to phi of MF, but that's just how we define it as phi of F, okay? So this phi is going to be left invariant mean on G, so your G is amenable by definition. So phi is left invariant mean, and therefore your G is amenable, okay? So this finish this whole cycle of these equivalences. And I just want to point out that, what I did in this course is we really just focus on the discrete case. So a consequence of these kind of equivalence is really a version of the Holinsky's theorem. So I'll just call it the discrete version. So a lot of these theorem we did in this course is going to still hold if you replace G by locally compact Hausdorff. The proof is just going to be a lot more uglier. Okay, so for the discrete version, I actually have the following characterization. So G is amenable if and only if basically what I have is that the reduced and the full are the same. What does it mean is that the left regular representation is really the norm you put in there is essentially just the universal norm. And because it's the universal norm, you have if you take any f inside the L1 of G, and you consider what's its norm inside using the left regular representation, that's going to be universal. So that's going to dominate all the other norm, okay? So you have the lambda f, okay? That's for all pi, you treat it as a representation of the L1 space, or you treat it as a unitary representation of G, okay? It doesn't really matter, they're really the same. Okay, so amenability really means your left regular representation has this universal property, okay? Its norm is the uniform norm. The proof is just really simple, okay? So the proof is just really simple. Amenability just implies that you can have some C star isomorphism from the reduced one to the full one, okay? Or because it's let's just use to the full one first, and then because the full one you can also compose it with some kind of homomorphism from this full one to the C star pi, okay? So basically you compose that, that's the map, and because that's norm reducing, and so the left hand side you take any lambda of f, you map to the universal one, so pi u of f, that's going to be isometric in fact, and you drop it to pi of f, that's going to only decrease in norm, okay? So let's finish the proof. And of course, this is going to be actually still hold even if you replace G by locally compact Hausdorff, okay? So I'm not going to prove that in this course.